So today we're going to be talking about how to determine the intersection between a line and a plane. So first let's think about what our cases can be. So option 1 is that the line intersects the plane at a single point. Option 2 is that the line is actually within the plane, therefore all of the points are in the plane. And option 3 is that the line is parallel to the plane and never will intersect the line. So in order to determine which situation occurs between the given line and the plane, we will substitute values from the parametric equations of the line into the equation for the plane. And so I'm just going to quickly remind you of our different forms. So for a line, we could have it in the form y equals mx plus b. For the plane, there is no equivalent representation that suits this format. It just doesn't exist, okay? We can have a scalar representation, which we talked about in the last class. And a scalar representation of the line or a plane is useful because from that we can easily determine the normal, which is the direction vector of the line perpendicular to the line or the plane that we're talking about. The direction of a line will only go in one direction, so we're only going to have one direction vector of a line. And a plane has two direction vectors, vector A and vector B. When we write parametric equations, we can see that the line only has one direction, it's going in direction A a certain number of times, represented by t. And a plane goes in two directions, so it's going in direction A a certain number of steps and B a certain number of times. From this we can write a vector representation which looks as follows. Okay, so let's look at our first case. So let's consider the case where the line intersects at a point, and let's see what happens to this line and the plane. So the first thing that we're going to do is we're going to write the line in parametric form. So I'm going to write line 1, and I'm going to write all about my x, my y, and my z. And so my x, my point, is 2, 1, negative 3. And the x goes in the t direction once, the y goes in the negative 2t direction, and the z goes in the plus 5t direction. And the question that I want to know is when does this line meet the plane? So when t is what? Okay. In order to do that, I am going to take the vector equation of the plane and substitute in these expressions. So here's my vector equation of the plane. And for x, I'm going to put the parametric expression for the line of x. For y, I'm going to do the same. Parametric expression of y. This should be a z. And for 2z, I'm going to put parametric expression of z in the plane. Okay, now I'm just going to multiply this out. And I'm going to combine my like terms, and I'm going to see that 21t equals negative, or so 21. If I add all those up, 2, negative 5, negative 6, and negative 12, and then put it to the other side. So therefore, this is happening when t equals 1. So likely, I'm going to want to find that point of intersection. So from here, I'm going to take, okay, so line 1 at t equals 1. What is that? Okay, and so I'm going to use my parametric expressions again. And I'm going to put t equals 1 into my value for t. Whoops. Now I know that my point of intersection is happening at 3, negative 1, and oh, sorry, this needed a negative sign. What's that? Not 8, 2. Okay, let's look at the next case. So in this next case, the line is actually in the plane. So let's see what happens when the line is actually in the plane. What's going to happen? So first, I'm going to write my parametric expression for my line. And this is my point, 7, -3, 8, going in the direction 3t, 1t, -2t. My vector expression for my plane I'm going to sub in my parametric expression. Oh dear. 13, -3 plus t plus 8, 8 minus 2t minus 32 equals 0. Okay, now I just need to multiply this through. 7, 3t minus 39 plus 13t plus 64. Oh dear. 64, there we go. Minus 16t minus 32 equals 0. And now I'm going to collect like terms. And when I do this, so 3t and 13t is 16t minus 16t, and 7 and -39 and 64 and -32 is 0. And I find out that t doesn't have to move at all for this to be true. This is happening because this line is already in the plane. So this line doesn't need to move in order for it to already be in the plane. Now, it is randomly possible that this is the point of intersection. So I'm going to do one more check just to make sure that this is in fact already in the plane. And I can do that if the direction vector of the line and the normal of the plane are perpendicular, are the same, so that when the dot product is taken of them, I get a 0. Okay, so I'm going to do a check because it's possible that just coincidentally I randomly picked the point of intersection here. And I'm going to take the direction vector of the line and dot it with the normal of the plane. Direction vector of the line is 3, 1, -2. Normal vector of the plane is 1, 13, 8. And when I do the dot product, if I get a 0, then these guys are perpendicular to each other. Therefore, the direction of the line is the same as the direction of the plane because the normal is perpendicular to both of them. Okay, so then I've got 3 times 1 is 3, 1 times 13 is 13, and -2 times 8 is -16. This does equal 0, therefore these lines are perpendicular. The line is in the plane. Okay, last possibility. The line is parallel to the plane. So we're going to do the same thing. We're going to set up line 1 in parametric form, starting from the point 1, 1, 1, going 4t, t, and 2t. When does this hit that? Okay, so I'm going to plug my expression for the line into the x, y, and z coordinates of the plane. Expand out my brackets. Collect like terms. I've got a 1, a 2, and a -3, and a 4. So that's just going to leave me with 4. And then I also have 4t plus 2t minus 6t, that is 0t. Okay, well, what is the value of t so that when it is times by 0, I get -4? And t Cannot. If I try to rearrange this, -4 divided by 0, this does not exist. There's no solution. No value of t will bring this line into the plane. Therefore, the line and the plane are parallel. Okay, for homework, we've got page 292 to 294, 1 to 3, 5, 7, 8, and 11.